So hey everyone, let's move on to the next question. That is sum of all odd length subarrays. So we are given an array of positive integers R. Calculate the sum of all the possible odd length subarrays which could happen. So subarray, if you don't know, it is a continuous subsequence of that particular array. So whiteboard explain this question. What can we think of that if you just go through example 1, then the output will be 58 because we can have 5 one-sized subarrays, that is 1, 4, 2, 5, 3, the elements containing themselves only. And then we could have 3 size subarrays from 1, 4, 2, 4, 2, 5, 2, 5, 3, and so on. We could have three such type of 3 size subarrays, and we could have one 5 side subarray which has a total sum of 50. Try to sum all of these, we'll get our answer as 58. Now, what we could think of is that we could have a brute force solution. So what we can do is 1, 4, 2, this is 5, 3. So what we can think of is that we try to increase the length of the subarrays which could be possible. So first we try to have size as 1, and we could generate all the one size subarrays. So we have an index that keeps a track of that particular window, and we'll have taking such elements, and once all of them are done, we could just increase our window from 1 to 3, and after 3 we could check all the 3 size subarrays. That means we could have this, we could have this, we could have this particular as well. After that, if when we are done with generating the 3 size subarrays, we would generate the 5 ones. So the 5 ones will be all these the only this subarray consisting of all these elements, and hence we are able to do it. If we talk about the time complexity, then we can say that number of window, that is if there is number is if the number of size of elements is 5, then we'll have to do it for at least 5 5 plus 1 divided by 2. That is, you have to solve at least 3 iterations, and for each value of k, that is the case, the size window, we'll have to uh, iterate this particular array again and again. So it will be order of n times k, n for traversing of all the elements, and k is for the number of window size. And the size, as we can speak, for 5 it is 3, so that means it's like it's n plus 1 divided by 2 if it is odd, and for even it is almost k is equal to n by 2. So for this particular thing, if we try to have calculate the final time complexity, we could say that it is calculating in the order of big O of n square. So as you can see, the order of n square is not a feasible solution, and we need to try to optimize this solution. So what can we think of? And here that we could just derive out some calculations. We could find some better ways to calculate that particular sum. So what can we currently think of? So we are given an array as 1, 4, 2, 5, and 3, and we need to calculate the sum of all the odd side subarrays. One thing that we can think of is that for each element which is occurring over here, it is occurring some particular times. If we know the number of frequency that that particular element is occurring in our answer, maybe that's the we could derive out our solution based on that. So let's just forget that we are required to calculate the sum of odd length subarrays. We try to generate for all length subarrays. Not we're not just keeping track of just odd. We are keeping a track of even length subarrays as well. So how many times can number one element be a part? So the number element, the one. could be a part of, I could say, 5 such subarrays, right? How did I derive this? We could have 1, we could have 1, 4, we could have 1, 4, 2, 1, 4, 2, 5, we could have 1, 4, 2, 5, 3, right? So what are we doing? So basically you're keeping a track of an index which is the start of that particular window of that subarray, and we are keeping a track that is the end of that particular window of that particular subarray. So in this case, our I, the starting element, was at 0, and our j, which keeps the end track of the subarray, was also at 0. So since this was at 0, comma 0, we only had one size subarray. If the j would have been 1, then it would have determined this array, this subarray. If the value of j would have been 2, then it would have been this 3 size subarray. If the value of would have been 3, then it would have been this, and so on for the next couple of iterations. If the value of I would have been 1, then it would have meant that we are starting from, instead of 1, we are starting from 4. And if our j is 1, it's I equals the same as j, means that this is the element we're talking about. If we try to increment our j from 1 to 2, that means it is talking about such subarray, and so on. So we can have an observation based on that, that the frequency of the element which is occurring is based on that number of elements that could occur, the number of elements which are to the left, which are the potential elements which could be considered as a starting index for that particular subarray. Also, we multiply it with the number of the the potential endpoints of that particular subarray. Right now, we are just keeping track of all the subarrays which could be generated. So, for example, for 1, we could say that we only have starting point as 1 available. Here, 1 refers to I is equal to 0. And we have 1, 2, 3, 4, and also the number itself. So we have 5 endpoints. That means element 1 occurs 1 into 5 endpoints. Why am I multiplying this? So if we have a couple of points like I is equal to 0, I is equal to 1, I is equal to 2, and we have j is equal to 3, j is equal to 4, j is equal to 5. So I could derive out different combinations having a particular starting index of that particular subarray along with a particular ending index of that subarray. So if I choose 0 and 5, it will mean the whole element of that particular subarray. If I do not choose, instead of 5 I choose 3, that would mean 0, 1, 2, 3, and only the 4th phase subarray. So I have potential number of start candidates, I have potential number of end candidates. So if I have n number of starting candidates, I have m number of ending candidates. I could just use and use multiple of them. Like I could just pick from one of them, that is NC1, and I could just take another one from this particular subset, that is MC1, and that just simply equals out to n cross m. So we have n cross m particular combinations that can be generated. Hence, this is a multiplication sign. Here we denote n for this, and this is m which I'm talking about here. N is 1, and I'm multiplying it with 5, which is the m value for this particular index. So for this particular index, we are generating for uh, we are computing this value, and we need to do this for each and every particular element in the array. So for 4, we could have two, like, let me just clear some screen, and then we'll move on for uh, the next iteration, that is I is equal to 1. So we are given an array like this. For 1, we computed that it is 1 plus 5, which equals 5. For 4, there are two potential start candidates, like I is equal to 0, I is equal to 1. And that means we have two potential sub candidates. Talking about the end candidates, we have 1, 2, 3, 4, that means 4. And we have 8. We have picked out the value for 2 cross 4 for the element 4, and this is for the element 1. After that, we could do the same thing for 2, we could do the same thing for 5, we could do the same thing for 3. And now here comes the part. We have tried to generate all the sums of all the uh, possible length subarrays. But in this question, we are required to find out the sum of only odd length subarrays. So when we have the number of elements is basically in the array is even. So we can just say that the number of odd sized element subarrays would be equal to the number of, if I denote the number of odd subarrays using odd and even using even, then I could simply say that even sized arrays plus odd sized arrays would generally define this possible combination of all subsized arrays which are possible. When the number of elements are odd, then I could say that we'll be having some, like as you can see over this particular index, this particular array, we have odd number of elements, that is 5. So I would say that there would be an extra element, one sized element that would be generated more, and that would just make the number of odd elements, it would be equal to even element sub arrays. Even here by elements I mean the even size sub arrays plus 1. So this plus 1 is because of the middle one size subarray, that in this case it is 2. So if it would have been 1453, then we would having the same number of subarrays possible. The only case that we won't be taking care of would be the subarrays which are generated using this particular element. So it would contain other subarrays such as 253 as well. It would have 425 as well, and 142. So the basic crux point is that if we need to get the odd length subarrays, then we could just simply divide it, just calculate the number of possible subarrays for that particular element, and we divide it by 2. And we do a seal division for that. Why seal? Because just in case the number of elements in the array are odd, for example in this case, then it should be a seal division, because the number of odd length subarrays is always greater than or equal to the number of even length subarrays. And why was the reason? I tried to explain it by taking the case of 14253, and because of the middle element 2, we are able to generate a lot of other middle-sized subarrays, because of which the number of odd length subarrays is either equal to the number of even length subarrays, or it is 1 plus the number of even length subarrays. So how can we just think of using these values? So if you try to multiply the number of the value of that particular array element, that is 1, to the number of occurrences that we compute, that was 1 cross 5 for element 1. If we just try to multiply it, we could get the number of value that would be devoting to our sum. Also, this is for all arrays. So uh, for of course for the generating the odd length of arrays, we need to divide it by 2. And why do we need to divide by 2? And we have to do seal division. That thing is already been explained. So can we just go on to the coding part, where I could see that so we have an integer answer, declare, declare answer, and I is equal to 0, I less than, and dot size plus plus. And here comes the computation part. So if we could just see that how are we doing this, we could just say that for the number of potential start points, if for an integer I, the number of potential start points, the number of start points can be I plus 1, because if suppose for I is equal to 0, there were n potential start candidates. For I is equal to 2, there were 3 potential candidates. For I is equal to 1, there were 2. So it's simply I plus 1. For number of end candidates, I would say if the number of elements are 5, so in the case of 1, we had possible of 5 end candidates, that is 1, 4, 2, 5, 3, and so, that we could simply call it n minus I. So if I is equal to 0, we'll be having n minus I, that is 5 end candidates would be possible. So, and then we need to multiply it, and then we need to take a seal division of 2. Why seal? That's already been explained. You could just uh, move on to any further discussions or solutions in order to get yourselves explained or acquainted with the fact that why is it seal division. So if we try to implement this, we can have int start value will be I plus 1, end value will be n minus I, and then the value that will be contributed will be we just try to declare it value is equal to start multiplied by the end value is possible, and then that particular value gets multiplied with the current value, that is array of I, and this is here will we have seal this which is 2.0, that particular the number of occurrences. This refers to the number of occurrences which the seal start into end divided by 2.0 is basically representing the number of occurrences in the odd length subarray for that particular element. To get the value, we just needed to multiply with the array element present in that particular array, and that's it. Just we just need to some keeper add it to our global answer that we need to return, and I think this would be I'm using something. This is n. Okay, this is n, so it should be add dot size, and for this particular test case, it's going good. And yeah, so it's being accepted, and this was the complete solution of this question. I think this is a good question. Like, uh, you can just keep a track of this question that why seal division is necessary, because when the number of elements are even, number of elements in the array even, and then the number of okay, it will be long description, but just in case if I need to explain this, we need to do the serial division. So because the number of elements in the array, if it is even, then the number of odd length subarrays and the number of even length subarrays would be same. And if the number of elements is odd, then the number of odd subarrays will be 1 plus the number of even element subarrays. So yeah, that's just it. And I think you could just try out on your own to generate some cases. So let me just give you an example for this. For element 142 for this particular subarray, we have subarray as 142, and we have again like we can have 142, one is array. So these are all the odd size subarrays that could be generated. So there is 4 in number. For even subsize arrays, we could have 1, 4, we could have 4, 2, and we have 2 for now. And yeah, so as you can see that type of arrays could be possible. We could have the number of odd sub arrays in this case is presently 4, the number of even sub arrays is presently 2. So you could just think of other cases as well, and you could just see that how is this problem happening. If you talk about 1423, we would have inserted another element. Then the number of even size sub arrays would have been 1, 4, it could have been 4, 2, it could have been 2, 3, it could be 4, 2, 3 as well. For the odd sized, we could have 1, we could have 4, we could have 2, 3 as similar elements. We could also have 1, 4, 2, we could have 4, 2, 3. So that means gives up to 6 elements. So as you can see, the number of odd size subarrays will always be greater than the number of even size elements. And why is the reason? Because I already explained it by using this condition. So apart from that, uh, let's move on to the next question. We could have, okay, so next question asks us to convert the binary number in a linked list to integer. So we're given a head, which is reference node to linked list. The value of each node in the linked list is either 0 or 1. The linked list holds the binary representation of a number, and we are returning the decimal value of the number in the linked list. So if we just go through these test cases, you might feel that, yeah, this is happening. 101. So basically, this I'm assuming this is the MSB and this is the LSB. If you just follow this particular case, I feel this is the, yeah, this is the MSB, because if this would have been LSB, then the answer would have been odd, because that would generate an odd value over, over at this particular bit. This is impossible. So of course this is an even, so that means this is an MSB. And yeah, that's just it. So simple one, we could just have int answer equals 0, and head while head not equal to null, or while head simple as that, we need to return, we need to do something while head is not null, and what we'll be doing, answer is equal to answer divided by 2 plus head pointing to that particular value, and try to, I think this will work. Head is equal to head connects. Yeah, it's working fine. Now we move on to the next question, that is find greatest common divisor of an array. Net connection. So we're given an integer array nums, and we need to return the greatest common divisor of the smallest number and largest number in nums. Okay, so the GCD of the two numbers is the largest positive integer that evenly divides both numbers. If you're talking about GCD, then it's basically just we're talking about the highest common factor. And there's a specific function for this. If you don't know, in C++, you have GCD, which calculates the integer, or we could just make it on your own. And uh, there have been various implementations for that, finding the particular GCD. So what we need to do, we need to just return the greatest common divisor of the smallest and the largest number in numbers. So okay, so we could just have two numbers, and we can simply return the here a equal track. This would be calculating the finding the particular element. So as you can see, the min element is basically returning that pointer to that particular variable, which is the minimum element. And if you're doing a star, we are just accessing value which is present. Try to do the same thing for this. We will be getting the maximum element, and then we can simply return GCD B, submit it, then it's working. Just in case, if you Just in case if you want to explore more about GCD, I would advise you to go through GFG and you can just talk about the implementations of GCD if you want to. If I just need to explain it, it's based on Euclidean algorithm, and it's a simple algorithm that a plus b y is equal to GCD of a comma b. So here it's just calculates the recursive relation, and using that you could just provide a recursive function for GCD where if the particular GCD is having inputs as A and B, then for the next particular series, you could just simply have B modulo A and the element as B, and it would do the same thing that it would be doing for the next recursive call as well. So that's pretty much it. If you could just move on to the next question, that is minimum time wasting visiting all the points. After that, we have Armstrong number. We could have uh, odd values. So right now, let's just move on to the next question. That is, on a 2D plane, there are n points with integer coordinates. Points I are present in x, y, and y. Return the minimum time in seconds to visit all the points in the order. Okay, so we have to visit all these points in the order, and the general intuition which is coming is like there are points like 1 comma 1, we have 3 comma 4 and minus 1 comma 0, 3 comma 4 we have minus 1 comma 0. So these are the points that we are taking care of. If you could just see that what are the uh, what can we think of, so if you just try to plot it over a graph, so I think here would be 1, here this would be 1, if this is 3, so some point 4, and here would be. So let me just talk about only these 2 points. So we are able to traverse diagonally as well. We can move vertically by 1 unit, we can move horizontally by 1 unit, and we can move diagonally. So any it these points can refer to any of any general points as such. Like you could, if you just try to rotate this particular graph system, it could just relate to any particular general coordinate system. If you try to just rotate the graph, there would be some position where in the orientation in which these points would be aligned in some way or the other. So what we can think of that, if we try to think of a greedy solution, then uh, at first I try to move diagonally, and once I'm not able to move diagonally, I try to uh, you know uh, cover that particular distance in straight lines. So what can happen is that what I'm trying to do when I'm trying to cover it diagonally, I'm basically from 1 comma 1 I'm going to from 1 comma 1 I'm going to diagonal, that is 2 comma 2, and then diagonal I come to 1 3 comma 3. So I'm trying to equalize any one of those coordinates with these coordinates. So once that x coordinate in this case gets equalized, then I could cover the remaining distance, that is 4 and 3. I could just simply do 4 minus 3. That means I need to cover one more extra space. So if I go here, that is 2 comma 2. If I go here, that is 3 comma 3. So this is 3 comma 3. This is 2 comma 2. Here it is 2. Here it is 2. It's not scale. Apologies for that. And here we reach 3 comma 3, and now this particular space is present, and we need to just cover it by using one space. So what exactly is happening? It's like we are calculating the minimum difference of these the differences between the x coordinates. So this is the difference between x diff, and this is the y coordinate difference. We take the minimum, and then we are trying to add something, and that something is basically we are trying to get the maximum difference of the coordinate value, and we are just decreasing this particular number. Now we have a simple approach for that. We are just seeing that if 1 comma 1 is 3 comma 4, so what can we do is we can just calculate the maximum difference which is present between these particular x coordinates and the maximum difference and the y difference between the difference between the y coordinates. So we can take out that maximum and that will be the maximum number of distance covered. In this case, 3 minus 1 was 2 and 4 minus 1 is 3. So the answer would be 3. Answer would be 3 in this case because we go from 1 comma 1 we go to 2 comma 2, from 2 comma 2 we go to 3 comma 3, and then from 3 comma 3 we need to add one more space in order to go to 3 comma 4. So this was using diagonal elements, and this was the vertical transfer. So 2, there it is 1, this is 2, and this is 3, so matches with the answer. So we just need to have a sum, have a answer is 0, we answer. Try to do is just is the point size, iterating to the point array, and points I1 minus points I0. Points I1 minus points I0. Okay. Points I minus I, it should be maximum of answer plus equal to maximum of two things. That should be I minus 1, 1, and the other thing should be points I0 minus points I minus 1. So that's just it. I think this will work. This is calculating the y coordinates. This is calculating distance for the x coordinates. We're taking maximum of these, and we are adding it to our global answer. In this case, I point I01 size maximum I1 minus. Okay, so I was missing absolute value. Grade ones. There should be absolute value because if we try to subtract a negative value from this particular variable, so it would be consisting of some value that might be resulting in a negative value, and that would not get us a maximum variable that is usually required over here. So we try to get the absolute values over here, and then we try to compare it. So try to just submit it. I think get submitted. Yes. The next question. Okay, so the next question is Leetcode premium question. For now, I'm not solving the Leetcode premium questions. I'm trying to solve all the general questions which are available on Leetcode norm profile. I think these questions are generally very sufficient and not to solve any other questions from premium. When you try to solve all the questions of Leetcode, then of course we could have time and then we could just spend some time on solving more premium questions. So for now, I'm just trying to solve all the normal questions that are available on Leetcode. If we have time, we could simply just discuss the solutions over of Armstrong number at any time if you want during the later part of the course. So for now, I'm just trying to that's done because I've already tried to solve this question. If you just go through any other particular resource, if you try to see the question, Armstrong numbers basically is a normal Armstrong question number which is asked that you're given an integer for that, an Armstrong number is a number which has the number equivalent to sum of the cubes of all the digits of a particular number. So if we just talk about examples of Armstrong number, I think 153 is an Armstrong number. I could just say 153 is an Armstrong number. So because a 5 is the sum of 5 cube plus 3 cube plus 1 cube, 5 cube is 125, 3 cube is 27, and 1 cube is 1. That adds to 153, also known as Narcissistic number by some people. And now we can move on to the next question, that is cells with odd values in a matrix. So we are given an m cross n matrix that is all initialized to all zeros. There's also 2D array indices where each indices represents a particular row index and a particular column index, and zero based indexing. And we need to perform such increment operations on a matrix. So if there is we're given indices, so it should do, it should increment all the cells which are present on that particular row R1, and then it should all increment all the cells which are present on the column C1. And after that, given m and n indices, return the number of odd values in the matrix after applying the increment to all the locations in the indices. Okay, so that's an easy question. I feel uh, so we're given m cross n matrix and all the values are initialized to 0. That's okay. What we try is we are given some indices, that is that, and indices 0 provides the row value and indices 1 provides the column value for each and every index. uh, so we could just see that if 0 and 1, 1 comma 1. So for row 0, this is see, this is the whole indexes array which we're talking about. So for r equals to 0, so let's just assume so for r0, that is this particular row, this whole row gets incremented to 1. So once this whole row gets incremented to 1, that is 1, 1, this is 1. Okay, so instead of 0, 1, 1, 1. After that, this column 1 gets incremented. That is 2, and this gets 2. Now this is one iteration of the index array. Now this is the first element traversal of indices array. So when we're going to the second indices element, that is r equals to 1, c is equal to 1, we increment the values which are present in row 1, that is 1, and this gets 2, this gets to 1, and the column value is 1 as well. So the column value, this goes to 3, and this goes to 3 again. And now when we try to get the total number of elements that have odd values, it will be 6. It will be all values because as you can see, uh, the matrix is 1 1 3 1 1 3 1, and hence this is the final value of the matrix. I need to calculate the odd number of odd elements which are present. So 1 2 3 4 5 6, so 6 elements. Then we need to return 6. One of the solutions that I could think of is a brute force solution. What can we think of? We just use that particular row, we could use that particular column, and we iterate through it every time, and we try to increment all those values. So we try to iterate over the matrix over r into c times, and that would give us a solution in, for example, if there are indices dot length, if the size of the indices is k, then we could simply call it n cross m. So OK cross n cross m solution. If you are trying to use r value as well, then of course we are fixing that particular r. So for that particular number of r, it would be uh, we would be doing it the number of c times, and for same goes for the column value. So it is just very large number. Like this shouldn't be done, and it's a like order of k cross n cross m, since here m into n is 50 each, and k, the maximum value of k would be 100. So I feel that this is the number of constraints are very low in this case, so this question gets accepted. Just in case the question constraints are very high, so this particular solution might fail for us. So let's not try to think of for solution. Let's try to think some other type of solution that we can think of in that has a lower time complexity. So what we are given is we are given an m cross n matrix. So m cross n matrix. So ultimately, what is happening? We need to keep a track of the rows which have odd elements and the columns which have the odd elements, right? So instead of directly updating over this particular matrix, we could have an m cross size row and an n cross size column arrays for both of them. So for m rows, we have two sized row array, and column size we have three sized column vector and an array that keeps a track of the number of that which row has odd elements and which row has doesn't. So if how does the row array get updated? So if we try to update it for the first time, so this row 0 gets updated as 1. When row the same row gets updated, it gets updated to 2, gets updated to 2, this gets updated to 2. And hence we could see that row 0, that is the first row of this, is not consisting of any odd values present. So in order to do that, so this solution isn't good for us. So we could have a flag variable or a boolean variable for each and every row, and that gets toggled. It's just like a toggle switch on and off. And if we are thinking of a switch, we can use a boolean flag for that, or we could have a boolean variable which when true signifies that when the particular row has all the odd elements. And yeah, after that, when we are done with updating all the row elements and the column elements, there would be some rows which will have contribution as an odd element, and some contribution that will have as an odd element, or it might be an even element. So the first step, let's just go over an algorithm, and let's just try to implement our first step. So what will be our first step? Our first step is we are updating row 1 and column 1. So row 1 will be updated to 1, column 1 will be updated to 1. For now, we are assuming that the odd value means 1. After that, when it is 0, we could use a simple XOR value for that. So what we can do is for row 0, increment it to 1, column 0, we increment it to 1. And then that's just it. Simply like nothing else is present, so this will be 0. Now we can see that row 1, row 0 has value of 1. The row 1 also has a value of 1. And column of 0 and the column of 1 has both values coming as 1. For this particular question, I could see that this is 1. So if you can just think of how to compute all those cells which have the odd values, you could have four cases. So if both of if the all the we have computed to get all the row values which have an even size value or an odd value which is present over that particular row. So row 0 of 1 means that row 0 has all the elements as odd, and same goes to the column. In order to get all the cells, what we can think of that we could have four cases. So if the odd row is odd, and if the row has all the odd elements and the column has all the odd elements, this would result in even. If you are trying to sum odd by odd, then it will get us an even value. If you have even row or odd column and vice versa, then we can say that it will result in an odd number. For even, it will be even simply. So we are just need to we're just concerned about these two cases. In order to generate those cases, after generating all this, after decomputing everything, you could just calculate the number of odd rows which are present here. You could calculate the number of odd columns, and we could simply do this basic addition multiplication that uh, we need to generate. Either we can have odd row, and using odd row we can have even columns, plus one case could be that we have even rows and we have odd columns, and that's just it. Like, that's is only required. So this particular case, in order to generate this, we could have uh, we are already given, like, this is odd row, odd columns, and the number of even rows would be the total number of rows, that is m, minus the odd rows, that would be number of even rows. The even columns would be n minus number of odd columns, that is 2, and hence we will be able to generate all those values. So this is something which is happening in a great time complexity and space complexity. So we have two integer arrays. One is for keeping a track of r, m0 value, we have of int, we have c, we have n0, and declare it by here. And then what can we think of is that we are using the vector indices. So auto using for each variable for indices, I could simply increment those values. So r of v0 plus plus, or I should just do it like r of v0. R of v0 is equal to r of v0 or 5, or of 1, right? And same goes for c1, c1. And what can we do is, once we try to get all those values, we have int odd r, which keeps a track of the number of odd values, the odd rows. Here odd rows means the rows which have all these cells as odd values. So trying to calculate the number of odd rows and odd C which is present. So for that we could just iterate over uh, I0 I less than m I plus plus if r dot I modulo 2, that is odd, just increment odd r plus plus, and same goes for calculating the number of odd columns for c I plus plus. Check if the number of values are coming in column plus plus. Once we try to generate this, I think we could simply return uh, odd row. It should be multiplied by the number of columns, the even columns, that is n minus odd c. We could have another case that is odd c into m minus number of the odd rows which happens. I think this will work. case, this is an error. N. Fine for this particular input. Let's just see if it works for the function as well or not. Yeah, it's running and it's running good. So we can just try to move this question. Here, if we can just think as a crux point, I could see that we could just pre-compute the values of individual rows and columns. I think this would be specifically fine for this particular problem.